In this activity, we'll navigate the unit circle. Number 1, determine the radian measure of each angle given in degrees, then plot the approximate location of the point corresponding to the angle on the unit circle. Okay, so let's try part A, 15 degrees. So we know that in order to convert from degrees to radians, we need to multiply by the right thing. The right thing is pi over 180. So let's go ahead and multiply by pi over 180. And then just reduce. 15 goes into 180 12 times, so we get pi over 12. That's our radian answer. If you type that into a calculator, you can get a decimal approximation. And then in terms of locating this point, so we know that this angle right here is 30 degrees. That's 30-degree angle in there, and we're trying to go halfway. So our point is going to be somewhere around here. So we'll just label this with 1A to indicate that's the answer to part 1A. Part B, 135 degrees. Same thing, multiply by the right thing, which is 180 over pi. Pi can stay, and then reduce the fraction that's left over. And we get 3 pi over 4. And again, if you want a decimal, you can type that in. And so you can think of this as 135 degrees, and that's fine, but you could also think of it in terms of radians. And we know, for example, that in terms of radians, up here at the top is about 1.57, and over here is pi. So definitely 2.35 is between those two numbers. So the angle is something in here. So 135 degrees happens to be one of the angles that's already labeled. It's this one right here in the middle. So this is 1B. Part C, negative 150 degrees, multiply by pi over 180, and reduce. Type it into the calculator if you want a decimal. And then in terms of finding this one, let's see. So it's negative 150 degrees. So we know that from here to here, that's negative 90. Negative means go clockwise. And that's an extra 30, so altogether here is 120. That's 15 more, so that must make this 135. And that's 15 more again, so that must make this negative 150. So that point right there is exactly the one that we want. Okay, and then finally pi degrees. Multiply by pi over 180 every time. So we get pi squared over 180, which you can type into the calculator and get about 0.055. And pi degrees is a very, very tiny angle. It's only about 3 degrees. And this angle is 30 degrees, so we want only 1/10 of this entire angle. So it's going to be pretty close to our starting point over here. So we'll call that 1B. Number 2, determine the degree measure of each angle given in radians, then plot the approximate location of the point corresponding to the angle on the unit circle. So this is the same exact problem as above, except going the other direction, which means we flip over the fraction we used up above. So here we multiply by 180 over pi, cancel, and we get 180 degrees, which is right here, 2A. Okay, 4 pi radians. So 4 pi, we multiply by 180 over pi. Pi's cancel, we just get 720. And hopefully we're starting to understand that if you do a complete revolution, that's 2 pi. So then 4 pi must be 2 complete revolutions. So the answer is right here, after 2 revolutions. Next one is 3 pi over 10. Multiply by 180 over pi. And cancel, and we just get 54 degrees. And we know that this line is our 30 degree, that's 45, that's 60, so 54 must be someplace in between these last two right up here. So we'll say something around here, 2C. Okay, and then finally 17 radians, which is a very big angle. Multiply by 180 over pi. And here we don't really get anything nice, so I'll just go right to the calculator. About 974 degrees. So what does that mean? Well, if you subtract off a bunch of 360s, in fact, subtract off two 360s, then you'll get some number that's between 0 and 360, which will be easier to plot. So it looks like this is really equivalent to a 254 degree angle. And we know that this angle right here, going from there to that line, is 240. So 254 is just a little bit past that one, maybe around here. Three, based on the unit circle above, find each of the following in terms of h and k. Note that all angles are measured in radians. So it's not actually above, but the unit circle is this one pictured right here. So what we're given is a point 10 and another point at an arbitrary h and a k, and then a generic named angle over here, theta. Okay, so the first thing we want to do is figure out what in part A it says is sine of theta. Well, we know that sine of theta is always the y-coordinate when you're in the unit circle. So the y-coordinate here is just k, and that's the answer to this problem. Part B says cosine theta. We know cosine on the unit circle is just the x-coordinate, which is h. But then things get a little bit trickier. So let's look at part C. Sine of negative theta. So if theta is pictured there, then negative theta must be this kind of point down here, this mirror image point. And I'm going to go ahead and label the coordinates here. I think it's going to help us. So the coordinates here, let's see, it's the same exact x as the other ones. So this must be h. But the y value used to be up here is k. Now it's down here. That must be minus k. So negative k goes right here. And so we're trying to find, in this problem here, sine of negative theta. Well, sine is the y value. Negative theta is this angle. There's the y value. It's negative k. And this is kind of leading someplace that we're headed. We have just figured out that the sine of theta and the sine of negative theta are the same number, but opposites each other. And that's something that's called an identity. It's true all the time for any angle you want. The sine of some angle is the opposite of the sine of negative that angle. Okay, so we'll see that soon enough. Next one is cosine of 2 pi minus theta. So let's see. So theta is this angle in here. So 2 pi minus theta must be the rest of it. 2 pi minus that angle. So it's all of this angle going out to here. So I'll just label that in purple here. So this angle is 2 pi minus theta. And thinking about it a little bit more, maybe I don't want to think of that purple angle as the one in question, but rather 2 pi minus theta is also going all the way around up until here. So that angle right there in green is also 2 pi minus theta. So let's get rid of this purple and say that the complete revolution there would be 2 pi, but we're going to stop it right there and say that this green angle is 2 pi minus theta. So the angle in question is this same one that we saw before, and the important points must be h and negative k. So we just have to grab the right thing. This is cosine of that angle, which is the x, which in this case is h. Okay, next one, sine of pi plus theta. Okay, let's see. So we know that pi is half a revolution. So then if I look at the theta that we've already got here, here's my theta angle, and if I go half a revolution from this line, it will land me down over here. So let's draw that in blue and say that this angle from here all the way around to here is pi plus theta. And labeling the points over here, it's gotta be h's and k's, so the only question is which ones are negative, which ones are positive. So this point is in the third quadrant, so clearly both coordinates are negative. And now we can do sine of pi plus theta. We know that the sine is the y-coordinate, it's negative k. Okay, next one, cosine of pi minus theta. Okay, let's see if we can find pi minus theta. So we know that theta is this angle here. So pi minus theta must be this thing. But having that angle here is kind of awkward. I'd much prefer it be coming from here. So what I'm going to do is, let's see if I have one more color. Let's go purple. I'm going to draw the theta angle here. And so what that means is that I'm saying theta is this angle, which means that pi minus theta, which is what I want, is now this angle in here. And that's a nice way to think about pi minus theta because it starts at the positive x-axis and goes counterclockwise, and that's exactly what our standard positioned angles do. So we're looking for cosine. That's the x, must be the x of whatever this point is. Let's label it. It's got to be h with h and k, and possibly some negatives. Let's see. We had to go left from the origin to get to the point, so the x is negative, and then we went up, so the y is positive. So again, cosine is the x is negative h is the answer. Okay, next one, sine of 7 pi minus theta. Let's do some rewriting here first. So going 7 pi around includes a couple of revolutions. So we know that 2 pi is 1 revolution. So 4 pi is 2 revolutions. 6 pi is 3 revolutions, which means that I can get rid of 6 of those pi's. Because they just involve extra revolutions that don't really have any effect. This is really a problem about pi minus theta. And pi minus theta we saw was this purple angle. So we're just going to use the coordinates up there that we've already got. This is sine, sine is y, so this problem has an answer of k. Okay, and then finally part h, cosine of 100 pi plus theta. So again, we know that every 2 pi is 1 revolution. So 100 pi is 50 revolutions. The important thing is not the 50, but that going around any number of times doesn't make any difference. The only part that we care about is the leftover part after we've done all of our complete revolutions. So this problem is really just about the original angle, theta. So here are the coordinates. We want cosine. Cosine is the x. So this one, the answer is h.